All right, good morning. We are starting Chapter 8. Chapter 8 is our unit on sequences and series. So, a sequence is a pattern of numbers, specifically, that we're going to be looking at. And then a series is the sum of those numbers. So, 8.1 is really just an introductory section. We're not going to get too specific in terms of some of the different types of sequences. We're going to look at all different types here and get used to some of the terminology. Okay, so for our first two problems, it says it wants us to describe the pattern, write the next term, and then write a rule, which is an equation for what they call the nth term. So if I wanted to find the 8th term or the 25th term, and when we look at our terms, this is considered to be the first term, the second term, the third, the fourth, the fifth, and so on. So our domain of our sequences is the set of counting numbers, right? We start with 1, 2, 3, 4, 5, and so on. All right, so when I look at this, trying to figure out how do I go from 4 to 24, from 24 to 144, 144 to 864, etc. And I want to be doing the same thing to get the next number in the sequence. So I could add 20. That would certainly get me from 4 to 24, but if I add 20, I don't get here. And so my next thought is, well, what if I multiply? And 6 times 4 is 24, and then as it turns out, 6 times 24 is 144, and so on. So in describing, I'm going to write multiply by 6. So for the next number, we are going to use our calculators. I don't expect you to have to do all of this without. So 5184 times 6. So our next number in the sequence is 31,104. And now when it comes down to writing a rule, I'm going to basically say, okay, there's my first term. And I'm going to write f of n. We're going to use n as our independent variable, n representing where we are in the sequence. My first term is 4 times 6. Now, I have to have a variable, so if I write n, right, because this is exponential, because we're multiplying to get the next number in the sequence, so we go back to chapter 6 when we were looking at some of these similar problems. The problem is when I plug in 1, because that when I plug in 1, I should get 4. If I plug in 1, I'm going to get 24. When I plug in 2, though, I should get 24. But when I plug in 2, I'm going to get 144. So what I need to do is an n minus 1. And then here, these are the inputs or domain. Here's the outputs or the range, the number in the sequences, or the numbers in the sequence rather. So now look, when I plug in 1 for n, 1 minus 1 is 0. 6 to the 0 is 1. I get 4. If I plug in 2, because this is the second number in the sequence, 2 minus 1 is 1. 6 to the first is 6. 6 times 4 is 24. If I can continue, if I plug in 3, 3 minus 1 is 2. 6 squared is 36. 4 times 36 is 144. So that fits. All right, so here I'm looking, and how do I get the next number? And I can see the pattern more clear here maybe, but I'm adding 100. So the next number in the sequence would be 475. And writing our rule, again, f of n. So now I'm adding, so this is going to be a linear equation when we're adding, and that linear, that 100 acts as a slope. So the first term is negative 25, and then I want to add 100. And if I notice, if I put 100n, because again, the slope is how much we add to get the next number in the sequence. You'll hear us talk about calling that a common difference. But if I plug in 1, I actually get the 75, right? Because negative 25 plus 100 is 75. I get the second number. If I plug in 2, I'm going to get the third number. So again, here we're going to do an n minus 1. Notice again, if I plug in 1, I get 0, which gives me the negative 25. If I plug in 2, 2 minus 1 is 1 times 100. And we get the 7 plus the negative 25, we get the 75. So, all right. The next one just asks us to find the next 3 terms. So again, we're looking for patterns. and I can see that I multiply by -4 to get the next number in the sequence. So now I'll go back to the calculator. I have -1024. Whoops, I wrote a decimal point there. So -1024 times -4, 4096. I'm going to just do times -4, right? And that, see how that brings up the previous answer. So -16,384, and then times -4, and we end up with 65,536. Okay, here I'm looking at a pattern. I'm saying, okay, let's see, maybe I add 2. What do I do here? Okay, so it looks like I add 3, I add 4, I add 5. Okay, so the next numbers are going to add 6, 7, and 8. So if I add 6 to 6, I get 12. If I add 7, I'll just write that out so you have that visually. If I add 7, I get 19. And if I add 8, I get 27. So there's, again, just pattern recognition there. Okay, finding the explicit formula, which is similar to finding the nth term. So we've done that twice here. We'll do that again. I'm looking, I'm going, well, let's see. It looks like I can see the pattern here, either multiply by 4 or add 6. And I'm noticing that add 6 seems to make sense. So I have -10 plus. I'm going to add 6, but again, we're going to do the n-1 so that when I plug in 1, I get -10. 2, I get -4, and so on. Here it looks like I am multiplying by 3 times 3 times 3 times 3. So my first term is -1, and then I'm going to go 3 raised to the n-1. So again, when I plug in 1 here, 3 to the 0 times -1 is -1. When I plug in 2, I get 3 to the first. So 3 times -1 is -3. If I plug in 3, 3 minus 1 is 2. 3 squared is 9 times -1, and that seems to fit. And there's a couple of other equations you could come up with. You could do this a little bit different, but I think that makes the most sense. All right, a couple more problems here to finish up section 8.1. Again, another one, write the explicit formula. So here we have a fraction. And what helps sometimes is to, if you have a whole number, to put it over 1. And I'm looking at this, and what stands out to me is that in the numerator, I keep adding 2. But the denominator, that doesn't fit. But what I see here are all perfect cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. And so sometimes we have sequences where you have different patterns in a numerator and a denominator, which is what we have here. So the denominator, 1 cubed, 2 cubed, 3 cubed, and so on, that would just be n cubed. And in our numerator, we're adding 2, but we start with 3. So 3 plus, and then 2, we'll do our n-1. So again, notice I go plug in 1, I get 0, so I get 3. If I plug in 2, I get 5, and so on. So there's our formula. All right, now evaluating a series. So a series is a sum of the numbers in a particular sequence. So this symbol here is a uppercase sigma, Greek letter. It means find the sum of. This is our index of summation, is our A. And what this is telling us is to plug the integers from 5 to 10 in for A and add all the numbers. So there are some formulas at times that we can use, but I'm just going to, these numbers are, there's not a long or wide range here. So just to show you what this means, so this is 100 minus 5 squared plus, because that means sum, 100 minus 6 squared, 100 minus 7 squared, 100 minus 8 squared, 100 minus 9 squared, plus 100 minus 10 squared. And all I did was substitute the integers from 5 to 10 in for A. You can see I had actually computed that previously. And when I hit enter, all of that is equal to 245. Okay, and now our last two are asking us to rewrite these sums into this sigma notation. So might as well start by indicating that. Notice that I go up by 5 each time. So again, I would have 25, the initial term, plus 5. And again, back to that idea that if I use n and I plug in 1, I'm going to get the second term. So we're going to do n minus 1. And so n starts with 1. There's your first term. Second, third, fourth, fifth, sixth. N goes to 6. Another way we could do this, and really this comes from distributing the 5, right? And then if you combine like terms, you could say n goes from 0 to 5 of 25 plus 5n. So notice when I plug in 0, we get 25. When I plug in 1, we would get 30. I like this one better because when you think about sequences, the first, second, third, fourth term, but sometimes you will see it written this way. Here again, we have another one where we're multiplying by 3 to get the next number. So there's our sum. Our first term is 1. 3, again, we're going to raise that to the n minus 1. And n will start at the first term, then the second, third, and it goes to the fourth term. Right? If I plug in 4 for n, 4 minus 1 is 3. 3 cubed is 27. 27 times 1 is 27. There's your fourth term. So there's our introduction to sequences and series. I hope that helps, and we'll see you soon.